Thank you for being here today. It's awesome to have such a big crowd already. I'm not sure how many you are there online, but welcome too. Today we're going to speak a bit about Python and Julia. I prepared a couple of notebooks which you can use to interactively join me today. And yeah, please, if you can turn on the screen. It's a bit small, but yeah, I also posted it in the Discord channel of this very room. It's the A0506. This is also the name of the Discord channel. And yeah, it's under Julien.io, Julien/io here, because in GitHub it's not possible. And then a workshop, Accelerate Python with Julia. And actually, if you go just to the GitHub organization, you already see it pinned at the top. So here, the fourth one. This is our material for today. We're getting more and more. So for those who join later, you can always point them to the Discord channel. So this is where it's now there, also for those who join in later, so that they can hook into our session. So if you are at this repository, yeah, I prepared kind of 3 points. Let's see, we cut a little bit here and there. So I think we make everything today, but I also want to have time for questions, so we'll be a bit flexible. And yeah, all this material is online available for you thanks to mybinder.org. I guess most of you know this organization and the lovely Jupyter notebooks it supports for us. And I'm also using this today. We have 2 introduction sessions for Julia, and then a final little example where I took one example from the web, quite recent, and put this into Julia as well, so that we can compare some performances from Python to Python, C++, and Julia. So we won't go into all the details here. The main part is that you understand it's actually easy to use Julia in order to speed up your Python code where you need it. Okay, so in case this happens and internet breaks down, on this very repo there's also a way to spawn the things locally on your laptop. The links will be a bit broken then, but you'll manage. Still, yeah, this spawns everything on your own laptop. You need Docker and Jupyter Repo to Docker for this, but it's really lovely. Other than that, it's the same environment. Okay, so we got a bit more, and because we only have 1.5 hours, it's not too much to get into a new language. I'm going to start into the first notebook. So I'm just clicking this very link here on the content page, and yeah, and this will open a new link. Yeah, so this should look similar for you. And I tested this before. If Binder was not kicking out my Docker cache, then this should start up within a couple of seconds. And yeah, we are lucky. The image is still there, and soon it's there. And the same should be kind of similar for you. Of course, it depends a bit on your connectivity. Also, Binder is not unlimited. I really hope this works. And in case it doesn't, there's always this local installation. And yeah, but it looks so far kind of okay. So I hope this starts within a minute at least. Usually it was a bit faster, but I think thousands are joining right now. So I open the pre-opened Binder. Wow, we're getting more and more. Welcome, everyone. So short words about me. I'm Stephan. Let me make this a little bit larger even. And taking out the view. Okay. So I'm Stephan Sahm. I'm one of the Julia enthusiasts in Germany. And yeah, about 1.5 years ago, I started my own company to offer Julia consultancy in Germany. It's called Julien.io. And yeah, it's progressing. Market is still very small, but yeah, as you see, there's a huge potential also in this technology. Even a bit longer, I organized the Julia user group Munich. Started 2.5 years ago, and we have kind of a monthly, mostly online setup because of Corona. The last years were a little bit online driven, so I'm very thankful to have this session in person again. And yeah, other than that, I came from academia, from stochastics, applied mathematician I am, and I also did cognitive science. That was kind of my study choice back then, which I really loved and I can totally recommend. Was in Osnabrück, cognitive science study. And yeah, if you want to chat, I also like to chat about philosophy of mind and this stuff. So yeah, really like these topics, but also stochastics and yeah. And from my daily life, I'm in the big data field and getting things into production. Okay, so let's see. So I hope. Okay, so this should have been up within a second. So can you give me a hands up? Who was able to get a binder running? Okay, these are a couple only. Who was trying to get a binder running but wasn't succeeding? Who failed so far? Okay, this is less. That's good. So sorry for those who have the same fate than I have. So apparently my binder. Okay, so fall back. So at least those who have this, they can join, and I will kick in the alternative and spawn it locally. So I pre-compiled it. The first time would be a bit longer for you because I already did it. I'm already there. And you should directly go to the notebooks itself. So, but I am now kind of in my local version of the binder. But actually now the other binder also came up. So yeah, just try it a couple of times. Okay, after this little introductory, how to get access to the platform, we are ready to start. And I would directly start because to lose too much time. But it's really, because we are here in person, it would be great if you have kind of some questions, yeah, please raise them. I try to do the best to be on track with the time, but I really like to take a couple of questions. So I need to calm down a couple of others if we get too much questions. But yeah, this is really one of the advantages to be interactive. Okay, first test. They're white in the back. I'm not sure how I can hear you, but give it a try. Yeah, so the link is on Discord. If you go to the Discord channel. Where do you find the Discord channel? That's a good one. Yeah, for the online audience, there were two questions about it related. So it's the question how to reach the Discord channel, and I don't know. Or just use github.com Julian. Yeah, you can. Yeah, that's probably the easier one then. If you go to github.com/Julian-io, this is the company GitHub, and there pinned you find the workshop Accelerate Python with Julia. You're right, this is actually a good shortcut. So Julian-io because of URL constraints. Okay, and then you can join us with the first part by clicking on the link in the outline. So let's go ahead. So we have these three parts I already mentioned, 2 times going into Julia, and one in the last part getting a kind of toy example, but still an example where you really get a feeling of comparing different languages. So let me get a bit more space. Okay, so one further question, please. Could you zoom in a bit, please? Yeah, thank you. So I hope it's better. Thank you. Question was to zoom in. You got it. So if you want to start learning Julia, I also have a couple of links at the end, but this one is kind of the most important. There's a learning section at the official Julia webpage, and there you can find a lot more information. So today we are mainly using one package. It's called Julia call, and this is my recommendation for you. It has kind of the best defaults to exchange between Python and Julia, and yeah, we completely focus on this package today. And we can, so I set up this environment, everything's installed. And if you installed it, you can from Julia call import main, and it's usually, or the documentation recommends this, and I like this, rename to JL, stands for Julia. And it has also a lovely IPython extension so that we can use magics, we can use cell magic and line magics to access Julia a bit more conveniently. Okay, so this has a little bit more output, and with this tiny screen, it's full in a second, but it's really kind of fast, just setting up a couple of things, and then we are ready to go, and we have this lovely Julia command. It's now the line magic, and if you execute the first two cells, you already have kind of a working Julia environment linked to the Python environment. And what we did here is just we activated the project this very notebook is in, to use a couple of packages which are defined in there, and we also allowed Python call, which is the opposite. So there's Julia call for the Python side and Python call now for the Julia side, and we use this to get everything working. So yeah, this little helper here, set var, is a tiny trick to easier get things from Python to Julia. And for example, now I have this little number of iterations, and I use this now from the JL, which we imported, and with dot I can now access anything in the Julia main namespace. And as we just defined a function here, I can now access it. So this is a tiny function definition in Julia, 2 arguments, and we are now setting them the key and the value, and this works. Okay, so one part of this workshop is to get you kind of deep into how you can interact with these 2 languages. Hence, it will be a bit dense here and there to get kind of the basics of Julia. But as you all know Python, I think this is not kind of a huge drawback, but you will get the language really quickly. You will see it's super similar. And if you're now a bit more of MATLAB even, then you feel more familiar. The syntax is actually more MATLAB-like. But yeah, from the style, you're working very similar to Python. Okay, so let's start. And in this introduction notebook, I just look into 2 things. This is the NumPy arrays and data frames, and it's super tiny, but still kind of gives you a good idea. So we set up a little NumPy array, which is actually up to 1,000, but yeah, we just print the first 10. So you can play a little bit with this number n and compare performances. But yeah, 1,000 is kind of okay to get a start. So this is here just Python, yeah? Here we are still in Python, and now we use the cell magic Julia, and now we switch to Julia. And in Julia, we have kind of this lovely add here, which is called a macro. This rewraps our code and does some fancy things. And this part here, it's very simple. It just also prints the name of the variables we put in. So you see here that we're printing also the name itself, and yeah, and this is impossible in Python, but a nice thing if you have macros available. So yeah, a little tiny thing. And what we do here, we set our NumPy array, yeah, via our set var little helper, and now we have it also in the Julia world. And you see that our Julia call and Python call was putting this into a special wrapper. It's called PyArray on the Julia side. So this is a good compromise. You can get kind of faster code depending kind of if you have a specific NumPy array with only floats, yeah, you can get a better representation in Julia. But this is a good general representation, and you also see it captures also kind of some type information about what is in there. And it actually has kind of good performance. So this is kind of now a little other function. We're just doubling things. In Julia, you don't need to put the multiplication sign between a number and a variable. just a little nicety. And this one is the first thing I want to show you, that in Julia, you can broadcast any function you define. So this is now a super tiny function. Yeah, it doesn't really make sense, but you can imagine, yeah, you have your own complex logic and you just want to broadcast it over your array. And in Julia, you just put a dot in front. And if you have multiple arrays, yeah, and they are different dimensions, then broadcast logic comes into play. If you've played with NumPy, you know this, yeah, then the other dimensions are filled up. And yeah, and this just works, and this is quite nice. And we can also show, okay, so this broadcasting now switched the time to the internal Julia array type. It's, if it's only one dimension, it's called vector. So this is just a little intro so that you see, okay, there's some care is taken about the types so that everything is kind of nice and works. And we also get a nice output. So this is standard Julia output. A Julia vector is usually a column vector. So a bit different than NumPy, but NumPy actually also supports column vectors. So there's also kind of a synergy. And because we just had a cell, I'm using this underscore to get access to the last return variable to see what this thing is actually on the Python side. And we see that this is a special class. So this is no longer a Julia vector itself, but it's wrapped into a Python thing. Here it's called vector value. But actually this gives access to the Julia side. So nothing is copied. Yeah, this whole Julia call, Python call is really to have no copy at all. And we just refer to the other side. And we can also make a copy, and this one here is now the next line. Yeah, if we just wrap it, many NumPy functions work out of the box with this vector value as well. Yeah, so you don't need to care so often, but in case you want to cast it explicitly to a NumPy array, just put it into a NumPy array, and then you are there. Okay, so here we got kind of 2 Julia and back for a little tiny example, multiplying it by 2 and again dividing it by 2. One question here in the front.
I just saw that there's a question online about the eval statement in your third block. Can you jump back up maybe?
Yeah. So online there was a question, an eval statement in the third plot.
Eval symbol K, Julia set bar, that line.
Ah, yeah. So this is a helper. Yeah. I promised you won't get all the details. So the evil one is just the normal thing where you can execute code in a language. So in Python you have this too. You can get a string, yeah, and I'm not sure where this evil exists, or not concretely, but you can execute an arbitrary string. And in Julia, you don't necessarily need to use a string, but Julia itself has a meta representation of itself. It's meta language like Lisp, and hence you don't need to always write this string. And with the macro in front, this is this @ sign. Yeah, so this always means, okay, here's some meta logic going on, rewriting the code. So this is, you can think of this like a string passed to the evil. But in Julia, we don't need to always use strings because we have this meta level. And then this is really just interpolation. Like in a string, you also have this, or on Bash, this $sign is always interpolation. And we put k equals y here as code and evaluate it. And because we get this as dynamically variables, we need to insert them somehow in this string, and then it gets executed first. So we actually have the variable n. Thank you for the question. And okay, so I'm going on. So where we've been, we've seen that we can go back and forth. And and now first part, this is all about speeding up stuff. So you will see a couple of mini benchmarks. And they are all somehow stupid, bear with me. It's also for demonstration purposes. But you'll see there's some truth for it, So take every benchmark with a grain of salt. It depends on the system, depends on what you do, how far you scale. But still, it's good, so we can time things and we can see, and if you have kind of a specific case, time a specific case, profile it, and you see kind of what is slow and what to speed up. So these are, we're using the IPython helper time it. This is one of the benefits of being in the Jupyter notebook. In pure Python, this is not available, but in Jupyter, thankfully, we have it in IPython. And we see kind of the standard list comprehension with 1,000. We have a couple of microseconds. And we can put the same range object to Julia and time it here. And bam, we see the first speed up. OK, so of course I made this. So I expect a couple of speed ups. And yeah, and interestingly, so if you put down the number of iterations to 100, yeah, then it's no longer faster, actually. So this is a typical thing. Yeah, if you have less iterations, then it may not make sense to switch the language. Yeah, so but if you have a couple of iterations, then it makes more sense. But actually, already for 1,000, we get kind of a good speed up here. Of course, this is plain Python. So let's look into NumPy. We have our NumPy array, and we can also multiply this by 2 and get the differences. And what we do here now is we always use this timeIt helper. And the timeIt is, of course, the Python side. Yeah? So if we now have the second test here, we go to Julia and go back to Python. Yeah? So this is, of course, a little overhead. And hence, yeah, actually, Julia is much slower here. But if we now want to test kind of the pure Julia, we can also do this on Julia itself. So this would not account for the switching. Yeah? Depending on the context, you need to account for the switching. So yeah, always mind what you want to test. But just for comparison, to see kind of what Julia can offer you, we're using benchmark tools. It's a little Julia package which has a btime macro and also a benchmark macro, which we're going to look into later. And I have 2 timings here. I want the double application to the NumPy array, and one time where we first converted to a Julia vector. So this is now pure Julia, and see the performance on the pure Julia array. So as you see, it's not so far away. Yeah. So we are kind of in the range of NumPy, depending on whether we use the NumPy array itself, a bit slower. If we pure Julia, a bit faster. But this is really kind of noise anyway. So these tiny numbers, they are kind of similar. So if you execute this a second time, you will see different values. OK, so that was the first benchmark. And I have another little benchmark just to convince you that there is some power behind. We'll see a bit more of that. And yeah, so what we're going to do here is just matrix multiplication. In Python, we have this @ sign, which somewhere came along to have matrix multiplication operator-wise. And in Julia, we just use multiplication because we have this dot for broadcasting. So for element-wise multiplication, you can use dot multiply. And yeah, and if we go the first time, so again, here we have the Python version. We are slower passing things to Julia. Doing the matrix multiplication there is slower. And if we do the same thing in Julia, now we get the speed up. Yeah, and this now is already a bit more drastically. So small matrices, yeah. So we have one, what's this actually doing is one vector standing and one vector laying, yeah, of 1,000. And we do the matrix multiplication here to get this down to a single value. And yeah, so this is already much faster than NumPy. Yeah, so take your preferred case, and now you can experiment a little bit. Yeah, if you have a NumPy thing which you often use, yeah, give it a try. Look whether you can just use this and already speed up stuff a little bit. So you see it's really tiny. And yeah, still, we're going to look this in a second. Yeah. So we, for now, have used the Jupyter helpers with the magics, the cell magics, but it's kind of the same if you're doing it programmatically. So you can really think of these benchmarks as something you can use right away in your Python code. Yeah. So it's just a little bit more handy now to use this Jupyter magics. OK, so this was intended to be interactive. So I put a little your spaces here and there. And as always, we need to be cautious about the time. And yeah, the first 30 minutes are already going to an end. So I think I'll skip this. I was expecting this to happen. I'm sorry, but yeah, you understand my situation. We want to cover a couple of content, but be invited. Yeah, go back to this Jupyter notebook and try a couple of different iteration numbers. Try your favorite NumPy and NumPy method and map it to Julia and see a couple of speedups. Okay, so. Yeah, so we still need to, I want to show you kind of what you would do if you don't have a Jupyter. So in Jupyter, we have this nice extra that we can also write files. And in this sense, you can think of this now just as a plain text file where some Julia code is in. And this would be, I think, the preferred way, yeah, to write a Julia extension, because then you have the best IDE support also. So you just write it in a Julia file, you just put it next to your Python code right there. And then from the Python side, you can call this special function string eval. We see the eval on the top. And now we have the evaluate also here with a string form. And in Julia, we have this extra command called include, just used as a function. And we pass the file name. And yeah, and with this, everything in the file is loaded into the current Julia session. And yeah, so the magic behind Julia is just-in-time compilation. So this is really optimal. Yeah, there's no difference in writing it before and loading it with Julia somehow, or yeah, calling the include. This is really the same. You don't need to be afraid that you get kind of some performance penalties. You can also use the seval directly. Yeah, if you prefer this, then you can use kind of standard Python, but mind that there's a begin and end needed if you have multiple commands. So tiny little thing, and it's always good kind of not to have too many obstacles. So, and then we can also call this little my function, and yeah, and what we have now is just we have the arguments and the keyword arguments, and we output them, and yeah, you see kind of some extra thing. We won't go in the detail here, but you see kind of how you can use it from Python itself. Please, one question.
Another question from the online audience. We've seen speedups with the multiplication operator. Can we expect these speedups for all operators, or is there a trade-off somewhere?
Okay, so the question from the online audience is that whether how the speedups behave, which we can expect if we have similar speedups like we see, like a factor of 10, and how to get an intuition where we get in a speedup, where not. And I think the best intuition is like the more individual you get, yeah. So if you have really individual tiny things you want to compute, then Julia gives you a huge speedup, yeah. Because all the NumPy ecosystem, this works by making things vectorized, yeah, and have kind of standard numeric types and crunching them on the C side. And Julia gives you the power to just define your own types, get everything in there, and have also the speed up on just a few iterations. Yeah, and this I think is where you can expect the huge speed ups. But still, Julia shows kind of a couple of extra speed ups if you plug in many tools. Yeah, so if you have kind of NumPy and you do a lot of things here and there, you still need to go to Python and back to C. Yeah, you have kind of some friction here and there. And the Julia side kind of also has an advantage here. If you have complex systems which need to interact, you get rid of this friction sometimes. But always kind of give it a try and benchmark it. That's the easiest to see.
And then there's another question online. Is the Julia code executed within the JVM, or do we need to take care / watch out for something in terms of exchanging from
memory?
JVM?
Yeah, okay, so the question is whether there's an extra Julia runtime, and it is, but it's, in this case, using Julia call, it's really kind of tightly bound to Python, so that we have the pointers going back and forth and not copying the data. At least this is the default. You can also copy the data if you want, but the default is not copying. And there's no JVM. So this is, not Java. Julia compiles down with LLVM, like C++ or Rust. So it's the C family on the Julia side. Okay, so yeah, last part for this year is to give you just a tiny thing for data frames. So data frames are also supported in Julia, and I just think that most of you use NumPy for arrays and data pandas or Polar for data frames. And in Julia, we also have data frame library, and it's also optimized for speed. So one thing in Julia is that people optimize for speed, so you can expect high performance. And so this is Python side, always mine, we don't have a Julia in front, just getting some example data frames. This is taken from this link where the data frames package in Julia has a comparison how you can get from pandas to dataframes.jl. And in Julia, it's quite similar. We actually have it a bit easier. We can use just keyword arguments directly to set up the columns. And the group by and mean looks massively different, but has a couple of advantages doing it that way. And both are kind of fine, but there's this link here at the top. This gives you a little table of how to go from pandas to Julia. Okay, so also a little benchmark here. This again uses our N. We just group stuff. It's just super stupid, but you be invited to get some fancier examples. So just 2 groups, and we sum up a couple of integers. And doing this on Python and doing this on Julia, we again see kind of a factor of 5 here. So it's again a super tiny example, but the key thing is it makes sense to give Julia a try if you want to speed up things. Okay, so again, a little tiny your space. Look into the link I put there and try some other mappings from pandas to dataframes.jl. Okay, this is the end of the first part. And I compiled here a couple of further resources where you can look into if you want to do more of this part. And next we go into another notebook format. I definitely wanted to show you this. It's called Pluto. And the main difference to Jupyter is that Pluto is reactive. But unfortunately, Pluto is Julia only at this time. So still, because this is also a Julia session, we can give it a try. So click on Next Notebook. This will open Binder. So this is the case. If you have the local installation, the links won't work. And this is because they point to Binder, but there's an URL path in the Binder part at the very end. And this is the thing you just need to place at the end of your local, and then also the local installation works. Okay.
You mean just the repo by local installation? Like, you mean
the repo to Docker. If you use the repo to Docker local installation like I did, then you just need to copy the last part URL path and place it into your what's here 127.0.0.1. So most of you will use Binder. For those, it's not interesting. But if you have the local version, okay, and okay. So I hope for most of you Binder still works, and I'm proceeding locally. Okay, so the Pluto notebook has a bit longer startup time than the Jupyter. This is a bit inconvenient in the beginning, but it's just a different kind of notebook. And one thing which it does is to execute everything in the beginning. So in Jupyter, you just start the Jupyter interactive shell, so you can interact with Python, and nothing is executed on the start. But in Pluto, actually everything is executed on the start, and this is why it needs a bit longer. And I prepared here kind of a notebook, which we are now going to look into. What's the timing? We have 40 minutes. Okay, so I think we are on track still. So the key things I want to show you in this notebook is actually how Julia managed to do this speed up. So Julia's unique advantage is that it's both simple and fast. And of course, there are also disadvantages. So how Julia does this is using just-in-time compilation. But yeah, this is kind of an abstract thing, and it's hard to think about this, how you can achieve these speedups with just-in-time compilation. And yeah, and this interactive notebook gives you an idea how you can use this and how Julia works to get the speed up. And yeah, so first little introduction to the Pluto notebook, and then to the 2 ingredients Julia has to get the speed up. So Pluto is interactive, reactive, so to say. If you re-execute something, everything else changes. And it also has support for some nice UIs. So it's a little slider, but you can build more complex stuff. And yeah, it's a bit tiny, but you see kind of things change. We change here the value of B by using this extra macro bind. More details at Pluto, pluto.jl. And we have another cell where we multiply it by 2. We have a little matrix here, which we define. And everything changes if we change something. And this is kind of the beauty. You more or less have just a code file, which is always re-executed for you. And yeah, and this last part here is just a plots heat map. So also plotting is in here. Okay, now to the 2 ingredients. So the first one, which makes Julia fast, are the so-called structs. This is also one disadvantage. Julia doesn't have object orientation, as you know it from Python. And this is mostly because of this performance reason. And what Julia has are kind of structs, which also can have a type hierarchy. But if you want to store some values, if you have some state which you want to handle, you only can store state at the very so-called leaf types. Yeah? So you kind of have an abstract type hierarchy, yeah? But these are only for overloading. We're going to see this. And if you want to store real state, you always need to take one of the leaf types, and you can't inherit from this. So this is the big disadvantage. If you love inheritance, then it's not directly mappable to Julia. But the advantage is that given this layout, the structs really have C performance. And we have here 2 structs, a cat and a dog. And you see here that we can also have some fields, and we can also assign types to the fields. By default, if you define such a struct, a field always has the type any, so it can store anything. But this is usually quite bad for performance. So yeah, you usually want to have kind of some type annotations. Then we can define some types. Yeah, so we have UTF-8 support. So we have a nice cat, we have a nice dog, and we can access the fields like normal. So this is the first part. And the second part are the functions. And yeah, just knowing these 2, you're already ready to define whatever Julia you want. Yeah. So the functions are, like in Python, generic functions. You don't need to specify types. By default, a function just works for any type. So if you want, this is a little bit like duck typing. And we here now see kind of a string with actually the interpolation syntax I mentioned before with the $, but now in a real string, not in a Julia code. And yeah, we just have a describe function here, and we can describe our cat, and we can describe our dog, and we just output this little string. We can also have functions with multiple arguments, as you see, yeah, and we can also meet our cats and dogs, and we have also the possibility to write generic functions which reuse our other functions. And this looks kind of super intuitive, and this is why Python is so famous, yeah? Because writing this kind of generic functionality is quite tough in statically typed languages, yeah? So in Python, you're used to this. This is totally normal, but it's really kind of one of the benefits Python gives you. And in Julia, you have kind of the same flow. You can just write your generic functions, and everything will work. And the nice thing about Julia now, so here this is our little story now. This kitty is Dexter, and kitty meets Dexter. And the thing Julia gives now in addition is that we can overload functions anywhere where we want. And I have here kind of uncommented a couple of lines. And if I now add this extra function, yeah, so I have a special function which now only works for dogs. So this is the double colon here and specifying the type. And now we know this is a dog, so we also have the name and the age, yeah, and can give a a little bit more description here. And you see everything else already updated, but because of the limited space, I need to scroll down. So we have this describe over here, which updated, and also in our little story, we also now got the right specialized function. So this is kind of the key idea in Julia. We just specialize our functions for the concrete types, and now the just-in-time compiler picks the right one. And we can do the very same. The describe one was now a single argument. We can also do the same with multiple arguments as we want. So if we now meet a cat with a dog, we also have a special thing which we want to print out. And you see it here at the top, at the bottom, that also everything else updated again. So this is the advantage of using Pluto, and we really have the special case kicking in. And if we do something else here, then we have the general case as a fallback. So this is the key idea behind Julia. We have, on the one hand, these structs, which are very efficient, and on the other hand, the generic functionalities. And we can specialize our functions to whatever we want, and by this, getting the performance benefits. And this is really the same mechanism which is used to speed up all the other things. So this is the key idea. Please, one question.
Two questions.
Two questions.
Online two questions. Regarding the structs, someone wants to know how these compare to Go's structs.
I don't know.
You know?
No,
Okay.
sorry. Yeah.
And then there's also the question, does Julia also generate bytecode-like intermediate representations, and how do they compare to Python's?
Okay, so the first question was how the structs compare to Go. I don't know. The second one was whether Julia used some intermediate representation. It definitely does, and it's some byte representations. And definitely it's different from Python, for sure, because it's in the C family. And yeah, but more details, I don't know. So what's interesting in Julia, you can actually define your own byte types. That might be a nice thing to be added here. So int, float, and all these things, yeah, they are actually defined within Julia. So there's a more fundamental byte type which you can use to implement all these things. But yeah, I'm sorry, no more details on the questions. Okay, to save some time, I think it's actually good to make a stop here. I just make a short thing over the last part. So here in this Pluto one, because this is the Julia side of things, yeah, I now went the other way. So I imported some Python here and doing some NumPy stuff here on Julia arrays. And yeah, and finally also a little performance test. And here a little example taken from Julia computing, a quite old example. I pimped it up for today's Julia. And this constructs Mandelbrot set. Yeah, tiny little example, but it also has kind of the specific part that you really have your own logic. Yeah, is this now part of the Mandel set or not? Yeah, this is a quite specific tiny function. So this is where Julia usually can give you a huge speed up to have some individual logic which you just want to implement fast. And we see kind of depending on how large we make this width of this little image, if we compute it in Julia versus Python, we get kind of a performance speedups up to factor 30. But also interesting, if we go completely down, yeah, Python is faster. So if you only have 10 by 10, then Python somehow manages to be faster. But for any reasonable size, Julia is faster. And if you go 1,000 by 1,000, I don't make this here because it takes ages for Python. Yeah, we have a speed up of factor 50 in this example. And yeah, you can kind of take a look at the implementations here. And the nice thing also, you see, I'm using a different interface actually, just that you know there are different ways to interact with Julia. I'm using PyCall here, while in the other part I would recommend Python call. But this little thing here is really nice. In Julia, we can use a pi in front of a multi-line string and then just have some Python being run. So in the sense, if I come from Julia and want to call Python, I really like this little string helper here. But the other way around, coming from Python to Julia, I prefer the other package. And hence my recommendation. Okay, so yeah, this was part 1 and 2 from the Julia introduction. Quite a quick one. I hope you're still with me. I now want to jump to the final example of giving kind of a performance comparison of this simulation example, but still, are there some questions for the Julia side here? Please.
Just another online question. Do you have some recommendations for what use cases you would want to go with Python Julia setup over something like PySpark, Dask, or something similar?
What would be a recommended application? Okay. Yeah. That's a good one. So in general, Python is kind of your tool if you want to plug and play. Yeah. So this is kind of where Python really shines because it is this huge ecosystem. So yeah, I think using Python as your glue language is kind of nice, works. And yeah, so for example, one thing I remember is that you have kind of some scikit-learn thing here, yeah, or you want to use some specific machine learning algorithm, yeah. You have a Python implementation, but it's somehow a bit crappy, yeah, I don't know. You really need to have it fast. So one way is actually really to re-implement the thing in Julia. It's not super hard, yeah. You can just go. If you really need this for production somewhere, this is an easy way. And chances are, because this is also the field where Julia is quite big, that someone else did this already for you. And then you can just use this implementation instead of the Python scikit-learn one, and you get some speedups. Julia is also well done for threaded computation and for multi-process computation. So it may also be that you find kind of a threaded implementation for your favorite algorithm in Julia, while there's none in Python because threaded stuff is a bit difficult in Python. Yeah, so something like this. I think it's a good example. Okay, so then I would jump to the last and final part. I'm glad you're all still with me. And now we're going to look into one example from multi-threaded guy. I definitely had this wrong. In a second, I have your name correct. So I took an example from the web where I think this is kind of a really good example. Okay, not sure what went wrong. So here we are. So for you, the binder link should just work. And this is the third one. Okay, so it's the multi-agent AI guy. So thank you, multi-agent AI guy, for giving me the core of this little example. I extended it a little bit here and there, fixed some things, and especially also added a Julia version. So what is this about? The multi-agent AI guy also made a nice little video. It's mostly black, but so what it's doing is to simulate just a couple of predators, plants, and prey. And they move around, and if they need each other, then they eat each other according to kind of some very simple rules. So this is the thing which we want to benchmark. And I think it's a kind of a good example because it's just a specific little thing. Yeah, you want some simulation of whatever to test something out, to get some error benchmarks, or to get some idea how it could behave. Yeah, get some intuition. So this is kind of a good thing. And simulation is also very individual and uses a couple of resources because you need to do a lot of steps, and you may want to speed this up and do this a million times to get some confidence intervals. I don't know. Yeah, so simulation is actually kind of a good example. The code we're going to look at won't output anything actually. So we really only focus on the performance comparison. But in this link I posted here on the top, there's also kind of a way to translate this then to a nice Pygame visualization. So if you want, you can also take this, and it's not so difficult to get this visualization out of it. Okay, so a new notebook. We again initialize our Julia setup in the back. And then we going to import some Python stuff. We initialize our random seed. I take this kind of from the example. Depending on whether you want to have it reproducible or just random, you don't need to do this. And we have a world width and a world height. This is the standard values from the blog post, and the timestamp, which I adjusted a little bit to have a bit more interactive Jupyter session, because things otherwise take a bit longer. Okay, so we now look into the Python implementation. We're approaching the first hour, and so it's a bit more code. Be with me, but I think it's worth it because it's really one of the examples where you also see how you can kind of map a type hierarchy. So I think this is a really good example to get an easy idea how to translate stuff from Python to Julia. So we have a Python agent class, which has a constructor, and it just initializes a couple of things. And if we don't give it a x and y, it gets a random start position. And everything is alive on the beginning, but it may die if it's eaten. And the key thing is here's an update method. So this very agent can eat food, and this logic just takes food and it eats it. So if you use this class falsely, then you have a plant eating a predator. But of course, we take care so that only prey can eat plant and predators can eat prey. And so with this update logic, there's kind of the simulation taking place. Things get older, that's nice. And we also chase a target, that's also kind of nice simulation. We choose, if there's kind of a target nearby, we kill it and get more energy. And if we don't have a target, we search for a new target. And then we speed up here a little bit, the movement. And we also, this is a bit later. And actually, if we have enough energy, we're going to see this, we're going to split up and get more of us. So it's a nice little simulation. That's just a tiny example where you have a couple of things. You need to be careful to do it right so that you really see something happening. But this was done. So thank you very much. Second part of this is kind of to execute the simulation. And because I'm using now also Cyton to compare, I put this extra classes here in the main method. That's one cool thing of Python. You just can do this. Put a class definition inside a function, no problem. So pure dynamic function, pure dynamic language. It's really nice that this works. Okay, so our main function then just initializes some prey, some predators, and some plants. And they just get randomly initialized. We only have this world width and world height, which we put in there. So it's really, simple, stupid Python. So 10, 10, 100, some constants. Just make it simple. And we have a couple of time steps. And this was set to 2000 now by me. But we can also set it somewhere to something else. We update everything. So we eat, in a sense. And then we filter all the things which died out, which we are kicking them out. We add some new plants every turn so that things are growing constantly and preys have something to eat. And if we have kind of preys which have enough energy, they split up so that new preys are going to be added to the field. And same for predators, but they need a bit more energy to get a new predator. So that was a quick one through this idea. So now you have the idea what we want to write. We wrote this in Python, and this thing works. And there's also kind of in the source code one alternative which was written then in Cyton. Definitely not optimal Cyton. So you can definitely take more out of Cyton, but just adding a couple of type definitions here and there, you get a little speed up. So okay, this was unexpected. I haven't executed the Python agent. Okay. So if we benchmark this now, I have this extra minus air minus r, which is the number of runs. You see that counting is quite difficult. Yeah, so we have 4 runs here, but still okay. It's very important because the Python one is the slowest. We have kind of 2.37 seconds. What is also important to keep in mind here, this is a simulation. Yeah, it's this really random stuff. And what is output here in the very end is the number of predators, the number of prey, and the number of plants. So you get an idea that these are really different runs. Yeah. So here we have no predators on the end, yeah, and tons of plants, and this kind of thing. Yeah. So yeah, take these numbers with a grain of salt, but still you see kind of a good improvement. And this is kind of a cool thing of Python. Yeah, we can just use this class and take it as a normal Python class and already get a speed up. So this is a flexible interaction. We can't do this with Julia, actually. It just takes too much time. But Python is well made for this object inheritance, and we can do this. It's already a huge speed up. So we can get a bit more. If we do also the main method in Python, we get a further speed up. And yeah, you see also there, yeah, this is important to see, okay, there are really different runs. It's not all 0, not all predators, but we have some good randomness. And we get another factor of, yeah, 2, let's say, yeah. So just also putting the main method into Python, we get another factor of 2. And now the C++ alternative, so thank you. This is also implemented by the multi-agent AI guy. There was one little thing, one little error in the C++ implementation. I need to make a post to him so that he can change it, so that the simulation is really the same. And so the C++ code gets compiled using G++, and yeah, then gives us an executable agent, and we can just time it here. I was not able to get the perf command running on this Jupyter. It was really difficult. So this I usually use for really timing things on the command line. But yeah, so we use the sub process and run our little C++ simulation. And you see that there's some difficulty here with the randomness. Yeah? So everything before was really kind of switching here and there, but still we have kind of a couple of things. So I think this is fine. And our speed here is now 60 milliseconds. So this is still a factor of 2 faster than the Python version. Okay, so that's the key comparison. And now comes the final part where we want to put this into Julia. Okay, so yeah, we have 30 minutes for this. And this is kind of cool. That's enough time. So you see my little your space advice, and it mentioned, please delete all of these cells. And I think because we have the time, I would like to do this. So this is the solution, yeah? And now it's gone. Okay. So yeah, so please be invited to do this with me. Now we're going to construct this in Julia. And I want to kind of give you the feeling that this is actually something you can do as well. So the first thing, and this is the most important thing, I think, which will pop up a couple of times, we have this type hierarchy. But actually in Julia, we don't have this type hierarchy. Yeah, we can just not simply inherit. So we have this agent at the top, and we have this predator, prey, and plants. So luckily, we don't do anything fancy here. Yeah. So actually, all these predators, prey, and plants, they just set this V max, the maximum speed, the velocity with which they can move. And yeah, we can just set this parameter by setting the value in the agent constructor. So what we're going to do is we just use one struct, one simple object, which has all our values, and we initialize it differently if we want to prey or if we want to plant. Okay, so hence the first step is to build kind of our struct. And I take this little thing here. So let's take a look. And I yeah, I'm going back here. So this is our Python agent, just a constructor. And we're going to move this to Julia. And yeah, in Julia, we don't have class, but structs. And we can call this Julia agent. And in Julia, we also don't have this colon at the end. We can inherit by using this little thing, and we can make it, don't know, an abstract array. But we don't want to. Okay, so everything is finalized with an end in Julia. Let's make this Julia. Okay. And now we can just put our field names here, like we've seen this with the cat and dog. And we can probably speed this up a little bit. And we would also like to have, yeah, this looks good. Yeah. So what's a little bit disadvantage in Julia is, okay, by default, we actually don't have this initial values. So if you just use this, it will fail. It's a bit unfortunate. But as Julia is quite powerful in the meta language, actually it's already very old. There's a little helper in the base. It's kind of one of these modules which are loaded by default. Most standard functions are in there. And most of them you can access directly, but for some you need to use the qualified access by putting base dot in front. And for the keyword definition, it's still the case for current Julia. And with this, yeah, we can use the default arguments. So, yeah, the world with, I also like default arguments here, and we already have these capital case versions we already have defined. And yeah, so now we are at the x values, and we don't have them set, so this is the default value, and we need to get some random number, and actually this is quite handy. In Julia we have the colon to make a range, and the rand function can pick us a value from this range. And this actually works, so we now access this other value here, and this just works fine if they are under another. And yeah, we can do the same here, and have this here. True and false are written lowercase. And there's something like none, but it's called nothing in Julia, also lowercase. Okay, then we have age and energy. So, and this is a good start. I think this is everything. Have I overlooked something? I think not, no? Okay, so now we have our type. And we can already test this so that you can get an idea this actually works. We can initialize this because everything has default values, and now we get our Julia agent. So that's the first part, yeah? So little helper here, keyword definition. But with this, it's kind of okay, yeah? So nothing super fancy. You can do this. Of course, yeah, you always need to do the mapping, yeah? If you have some Python stuff here, Google is your friend, or ChatGPT, and then, yeah, you usually get a good answer. Yeah, a little freaky, yeah. So you really need to do this this mapping. But okay, you can make it. It's just for speeding up a tiny part. Okay, so next part is to do this update, and there we already see kind of a little bit the spirit of Julia. In Python, we have this object function that we would now have this update logic somewhere here, yeah, within our object. But in Julia, this is just differently designed. We don't do this. In Julia, all the functionality, they are separate. So we really have this distinction of the structs and the functions, as I showed you in the Pluto notebook. And hence, we really do our update function separately. And we can define some types, like Julia agent, but we don't need to. Yeah. So remember, our update function always updated our little agent and get some food. And it's helpful to name our agent also self. So we now really have kind of the same namings as in Python. And what's also common in Julia is that we actually use an exclamation mark at the end if we want to indicate that something's mutated. And this is the case here. We have our agent and we mutate our agent. And this is kind of a nice convention. I like this. So let's put an exclamation mark in the end. Okay, update. So let's go to the top and get our update logic. So it's a bit larger, but we'll make it. And otherwise, we just take our solution. Okay, so it's the very same. Let's take this down one level and end at the end. So main purpose of this is that you see this is really intuitive. Yeah. So I hope this message comes. And yeah, let's see. So we have our update logic and we get some food in there. So this update here is the very same. Yeah, we can actually make this a bit more condensed. So plus equals also exists. So if we can't move, we return. That's almost the same. In Julia, we don't have this double colon, but we need to end things with an end. So if self-target and not self-target is alive. So this is a bit more complex because this means just a Python Boolean check, yeah, which is a bit fancy dynamic Python thing. And we know that our thing is nothing, yeah. So in Julia, we usually compare directly with this nothing value. This is our special part. So we have here a target, which is not nothing, so we have a real target, and end doesn't exist. We need to use double. This is also there in Python, I think. This double end sign, and not does also not exist. The exclamation mark is used. But the other thing is the same. Again, semicolon at the end, back, and the end. And none, of course, isn't there, so we set it to nothing. Okay, so this is the opposite. If self-target, it's again the same. So squared distance. In Julia, we really have this. I don't know the name, actually. So yeah, we can square it with the usual operator. Python has a special operator. And we need to get everything with an end. So false needs to be written lowercase. Yeah, these tiny things. Some of them can be automatized, but usually, it's speed up of a tiny part, so it's easily also done by hand. Okay, so why not? Let's make a plus equals 1. Okay, if not self-target, so this means if this thing is nothing, we do a for loop. For loops can be written similarly. We just don't have this colon at the end and get everything finished with an end statement. Is not existent. You use the same like we did for the nothing, the 3 equal signs or exclamation mark within, and here again the end. And you get the idea. Yeah. So this is the thing which you do then, but other than that, it's really kind of easygoing. The semantics are similar. Yeah, it's really a dynamically typed language. It's just in time compiled. But the flow it goes is the same like in Python. You don't need to care about static types. It will just work the same. The static types in Julia are really just for speed up. The thing will do the same, just slower if you don't use the type information. So you can always be sure that you can just work like Python, and then you add some types for speed up, but you don't need to care for them. So it's the same flow as in Python. So definitely I did some, it looks good, okay. So we have this self-target, if this exists, so these things. And I think I will leave it by the update method and copy the main method from the solution. It's straightforward, but it takes some time. So I ate one of these. Okay, so there we are. Okay, so this is our update method. This was it. And we mutated a lot of the self, and of course this is Julia. So we need to do this in Julia. Okay, that's a bit tedious, so I now go to the repository and go to copy the main method. Of course, you're invited to do this really by hand and experience it. But yeah, so let's copy the main function. What's the time? Yeah, okay. So there we're back. The main function, let me explain to you kind of what are the key parts for this translation. So Julia also has keyword arguments, but you activate them if you put a semicolon in front. So this is a tiny little thing. So this is, in front you have kind of the positional arguments, yeah? And after the semicolon, the keyword arguments come. And in Julia, this is important to distinguish because you have this overloading, yeah? You can specialize the functions for arbitrary types. And the specialization, this only happens on the positional part. Still, it's very handy to use keyword arguments if you just want to write an interface function, yeah, like such a main method. So yeah, it's well supported, and you also don't need to be afraid that you lose kind of performance. Yeah, this is also all type supported. Yeah, it's just, if you use Julia a bit more, then this is kind of standard, but in the first side, it looks a little bit alien to have this semicolon in front. But then it's just normal Python syntax as well. So we initialize here a show function to get rid of some printings, but then we have this world with world height and timestamps. And this is kind of one extra thing. So in Julia, you get the speedups if you use functions. And these world width and world height and timestamps, they are defined globally. Yeah, we just assigned them to our global namespace. So Julia supports this, that you can use this. But the global variable is like a black box for Julia. This is, you can implement some fancy logic with this. Yeah, you can assign the global variables from some other thread and then take it again. Yes, you can do fancy stuff with it. But in Julia, usually these global variables, they have the type any. And this is handy, but it can kind of cut down performance. So actually, if we used the time steps, for example, here, we have this while loop. It will check every time, okay, my time steps, global variable, have you changed in the meanwhile? Oh, no, you haven't changed, but it really does now, and it will always check, okay, are you still of the right type? Are you still int, And interacting with global variables, has some performance impacts. So the thing which you usually see is that you just put them like here in function arguments. So as a default value here. So the function will be initialized, and then it knows, okay, for this function execution, my time steps is really an integer, and it's really this value. And then Julia can do all the rest. It's a tiny thing, but just good to know. And as you're here to learn this thing, I think this is kind of a nice little extra. So tiny little helper gives you some speedups and looks good, so you can also parameterize it. Other than that, we have kind of keyword arguments, and we use also named tuples. You see, this is the very same syntax as here with the semicolon in front. And actually, we don't need to write out the extra part. We can just leave it, and it will take the name as it is. So this is a kind of a shortcut. Then we initialize everything. Same, we have the for comprehensions here, and again the semicolon to use the keyword arguments. But otherwise the same. We have the time step, we have the while loop, we have a for loop to update. Now we use the exclamation mark method here. And we filter. This is a little speed up in Python. You can also kind of do a for comprehension again here by filtering with an if statement. But it creates a new array. And actually the C++ version also just filtered. So I thought it was fair to also use the filter version here. We append, we go through it, for loop, filter, push, append to the arrays, and this is kind of it. So it's really the same idea as in Python, just tiny mapping between functions. There's one question over there. Thank you.
Could you elaborate once again on this, the constants or the word height or width?
Yeah.
If you would use it badly in Python, for example, like you change the value along the line, then it would be the same in Python, the same problem in
Yeah, so Python doesn't care so much because it doesn't check the types to improve performance. And in Julia, this is really done every time. And we're going to see this actually. Yeah, so it's really for the compiler. It will work the very same way in Julia, it's just slower. And the more this type information is available, the more Julia can actually optimize its code on the fly. Thank you. Please, one further question.
Yeah. So in that context, with the keyword args, you were overwriting the word with word height settings in the individual agents. So the initialization we did in the agent class itself doesn't have any effect at all. Could have been nothing or whatever.
I'm initializing it here, but you're right. Yeah, I did give a default over there. Yeah, no, this is not used. Yeah, the question was, thank you for reminding, that above we defined our nice struct with some default values, and also for world height and world width, we don't use it. Yeah, so this is correct, and yeah, it's just this, yeah. I think this was part of the translation to Julia, and then it doesn't make all sense, but it's good enough. Thank you for the question. Okay, so there we are. Yeah, everything is defined, and now we can run it. And this, the super interesting part. Okay. Let's take a look.
I think you have defined your phrase validators and classes.
Correct. Thank you. Okay, so let's do this here on the top. We have our Julia agent. So there was a comment that I haven't defined the sub parts, and there's a nice little thing. So it's super quick defined. And does someone of you can tell me what the values are for the keyword Vmax?
2.0 and 0.0.
Okay, for the prey, please.
2.5.
2.5. Okay.
Sorry, 2.0.
2.0. Okay, so order is random, predator,
2.5.
and plant. So you see this one is really simple, isn't it? So we just overwrite kind of one of these default values, and we got rid of inheritance. Bam. Okay, so let's check whether this works. Of course. Yeah, good one. 10 minutes left. We get there. The default struct in Julia is unfortunately, is intentionally immutable. And you need to add an extra mutable command to really make it mutable. And because the structs are so important in Julia, they actually cannot be redefined if something like this crucially changed. You need to restart the Julia session. And it's a little disadvantage, but I think it's because of optimization. So I renamed it now to get rid of this difficulty. Okay, last try. If it doesn't work, I take the other solution. Okay, I take the other solution. None is not defined. Have you seen a none? There, none. Come. I'm so motivated. Math is not defined. So we used a math function somewhere, square root. Square root is just normal. Yeah, we don't need to use math. It's one of the standards. Looks good, doesn't it? Okay, so key thing is, this is slow. And this is still a bit faster than Python. I think Python was a bit more than 2 seconds, yeah. But it's really slow. We're definitely not at the 60 milliseconds. Yeah. And now comes the last piece, and this is the type information. And yeah, and this is kind of the crucial part. So you see, yeah, this is really just 1.6 seconds. And C++ was 60 milliseconds. So we really need to speed this up. Otherwise, this would be a terrible workshop. And the key thing is, it looks almost identical, yeah, is that we add some type information to our struct type. So it works, yeah, and it's all fine, but it works just much faster if we add type information. And I again changed the name to not confuse Julia. And yeah, it's the very same, just added some type information here. And yeah, and we have some special thing here. The agent is a union of a nothing and an agent, so that we can set it to nothing. And this is, of course, a typed agent now. I need to change. OK, so sure, this is Julia code. OK, and no. OK, so let's take a look. Damn it. OK, so I did some extra adaptation somewhere. So I need to also get the update method ready. So it worked for the standard case, but because we set the type, we now have kind of some type conversion kicking in. And yeah, and apparently this was not accounted for in my little spontaneous version. So I just overrode it, yeah. So this is also super awesome in Julia. We can just override a function and it will pick up the new one. And now, bam, this should be faster. Okay. So I can't, yeah. Okay, so this is very optimistic, yeah. So we are now down to 4 milliseconds. And there's another macro benchmark, which we haven't used so far, but now it's quite nice. And they also turn off the output. And there we see kind of a little bit more the distribution. And we also see information about garbage collection. And this is kind of key thing, which also is kind of difference between Julia and C++. There we don't have the garbage collector. In Julia we have it, which is, yeah, depending on your use case, an advantage or a disadvantage. But for just quickly typing, it's usually an advantage to have a garbage collector. And here you see kind of we ranged from what we see above. This is kind of our minimal case with almost zero, yeah, with zero garbage collection to something around 63 milliseconds, which was the C++ timing, roughly, yeah, if our garbage collector kicked in a bit more. And median time here, 46. OK, so I'm glad we came to this point. Yeah. So this is kind of the key idea. You can speed up even more Julia. Yeah. So we now just added kind of the type information in the struct. Yeah. This is kind of the key part, the interface, so to say. Yeah. Which is then handled. But of course, Julia is not of course, but Julia is really meant for high performance computing. So there are a couple of extra things you can do. Yeah. You can turn off bound checks on arrays and stuff like this. You can really get low level and get more speed out of it even more. So this is kind of the standard, yeah, speed up. And if you really like to get more performance out of it, there are ways to do that as well. Yeah, so OK, I think this is good. I have kind of 2 minutes left. So there are a couple of further resources here. Follow me on LinkedIn, and you can also reach me at my email. I'm very glad to have had you today. And we have 1 minute for questions, for further questions. Thank you for being with me today. It was a pleasure. One question from online.
How does Julia compare to the just-in-time compilation with Number?
Yeah, Number is awesome. Yeah, same approach. Number is kind of restricted to a sub-language of Python, same as JAX. So yeah, and yeah, you just need to confirm the sub-language then you get probably similar speedups, but you still have this friction with Python itself. And in Julia, it's kind of default. All custom types are there, and you don't need to care about this language difference.
And then there's another one. Would you recommend using Julia as a backend for a Python package? If so, can we get a binary package so that the user doesn't have to install Julia first?
Yeah, awesome question. So this is actually in the summary. You can actually compile Julia down to a C library. So the question is whether we can get rid of the Julia executable. and we can, but this usually doesn't make sense for this experimentation. Yeah, so just Julia is downloaded for you with these packages, and it runs. But if you want to get to production and you want to get rid of the Julia part, you can do so and compile Julia to a C library. 2 minutes. Okay. I'm not sure. Question over there, please. Yeah.
We saw that we could like use different data types within Julia, like dataframe and NumPy. How would you go about if you have a code with a lot of more specific libraries, like image modification, like CD2? Would you use this in Julia?
So the question is how to deal with other individual types, how they are mapped. I have no experience, to admit. Yeah. So in general, they are just pointers to the Python objects, and then you kind of access the Python objects. And if in this complex thing there somewhere is a NumPy array, you can still access this and use kind of the NumPy speedup. But yeah, in general, I think you have kind of this slow access until you have the data you want, and then you run in Julia, and then you output kind of something, and this workflow should work with all custom types also. Yeah. One question over here.
Yeah, if we talk about machine learning, for example, and most of the popular algorithms are implemented still in C, right? Usually.
Yes. Yeah.
Python, wrapper Python, and if the same implemented in Julia, so that performance boost. If you compare with the C implementation, with C++, but C.
Yeah. So the question is whether how to compare Julia performance with C, especially with machine learning. I think performance is very similar. And usually, the code is much, much smaller because you have this support for exactly this applied mathematics. Yeah. So you can expect similar performance. And depending on how good the C code is written, the Julia might be faster. Yeah. Okay, so this was it. I'm here for further questions. You see me, I have this nice Julia thing here. And so thank you for being here, but you can also come here to the front and ask more questions. I'm there. Our time is over. Thank you again and see you at the conference. Enjoy it.